Yeah, so remember to do the evaluations. I think I had them set till tomorrow at noon or 5 or something like that. But get them done. I've got to be doing some traveling also, so get the homework to me as soon as you can. And if you get one done, don't give them to me in batch. Just submit it as soon as you got it done. That'll help me along. If you don't get everything turned in, I will grade you on what you got. And if you don't like it, I'll call. We'll see if I can Gandalf it if you've got the other stuff done. So, okay, any questions? Okay, so the last thing we talked about was what I thought was like a super cool thing. I want to see why this is true. We built up a little bit to kind of for this. Then the interval closure bar. So in other words, the interval closure bar is just the intersection of all valuation over. So here, of course, I didn't say K is quotient field bar. The interval closure bar is the intersection of its valuation overlays. So valuation domains, these are things that we remember giving you pair of elements, one divides the other. We also noted that this there's this thing called valuation on the field, and the valuation domain consists of elements that are non-negative there. By the way, if you're interested in my course in the fall factorization techniques, we'll probably go over this a little bit, and I haven't completely decided yet, but of course, if you wanted to do this, we'll probably talk about the p-adics and valuations, some geometry, etc. But anyway, I've always found this fascinating. You have these domains that are almost fields in a certain sense, right? They've got this valuation on them, giving you a pair of elements, one divides the other, and their intersection actually determines the interval closure, right? So, see two sort of singular unrelated things. This is the easier direction. This is sort of warm up, right? Why is this true? So suppose omega and K is interval over R. What does this mean? It's a root of some monic polynomial whose coefficients happen to be in R. Then omega is integral over every D that contains R. Well, because if the coefficients come from R, then they certainly come from R D as well. Agree? So the interval closure bar is contained in the interval closure of V. Because R is in V, so the interval closure bar must be contained in the interval closure of V. And what do we know about the interval closure of evaluation domain? Right, it's already interval closed, right? So the result of evaluation domain is closed. So R is contained in the intersection of all evaluation domains. That one's Easy peasy lemon squeezy. What about the other direction? Let's look at the other direction here. To me, this is the interesting part. How does membership in a bunch of valuation domains mean that you're integral of things, right? By way of contradiction, suppose that omega is not overall. Anybody think of what a characterization of integral that we talked about that might be useful here? You might think of any other characterization of integral. Root of Monte polynomial. What else we got? That's a strong thing, right? Finitely generated. There's finitely generated R mod such that omega times n is contained in. There's that. Is there another one? Do I remember anything else? I think that maybe Grant did this back in the day. I feel myself having to appeal to him a lot, right? A crucial day for me to be gone, I guess. But omega is integral. If and only if omega is contained. Does anybody remember what it is? How about this? I actually maybe I didn't do this. Does that rebel y'all? Right, because if omega is in R adjoined with, so let me kind of go through this just to make sure that we're all on the same page, because this is actually crucial in the proof. So if omega is in here, then let's say R, omega minus 1. That's what the statement means. Omega is a linear combination powers of omega inverse, right? And so you might guess what I do here. I can make this all sort of non-negative by multiplying by omega to m. And then taking things over to the other side. Which is, of course, Rm. So omega is integral. And the other direction is basically the same thing. You just take the integral equation and just reverse this argument. Everybody okay with that? Okay, so I predict this characterization is going to be important. Why? Well, let's suppose that omega is non-integral. Okay, so how does that help? So omega doesn't live there. So let me ask you a question then. Omega is not in the smallest ring that contains R and the inverse of omega, right? What does that mean about the status of omega inverse as an element of that ring? Well, let me ask you this. What is the status of this ideal? course, I can take any ideal, right? I can pick any element here and see the ideal generated. What does this say about the status of what's true about that ideal? Can it be the whole ring? It cannot. So I'm looking for something simple here. Right. This is a proper ideal. Agree? So if omega doesn't live here, that means that it's ideal generated by omega inverse proper ideal. So okay. So this is a proper ideal. What do we know about ideals and rings and valuation domains? Those are that is correct. Let me state the question a little bit more correctly, or a little bit more clearly. If I have a ring and a proper ideal, what's a big theorem we had about valuation domains concerning that ideal? Right, so the ideal may be an ideal of a smaller ring sine field. Then there must be, if it's a proper ideal, there must be a valuation overring where that ideal survives. Very good. So there exists a valuation domain. Call it W, such that W contains R omega inverse, which of course contains R, and omega inverse survives. And does anybody see what the problem that is? There's some serious problems with survivor here. We're gonna have to vote somebody off the island pretty quick. And who will that be? If, since it survives in W, of course, that means that's a proper ideal. What's one thing in the quotient field that therefore cannot be in W if that idea survives? Right. Omega is not W. Agreed? And this is a contradiction. Because we have W is now the evaluation domain containing R, but not omega. Right? Because see where omega lives, we looked in every valuation over omega part. Agree? So omega is in play. And we have both components. So we now have R bar is equal to R. Okay. Any questions on that? Okay, I'm going to get to, so my plan for today is I want to talk about invertible ideals. These are actually important in number theory and in Dedekind domains, which one can argue is the global version of what well, so a global version of the theory of valuation domains. And I'm going to talk a little bit about the connection with number theory and get to more of this if you have a class in the future. So, how many of you have ever heard the concept of, so let me run some buzzwords by you. How many of you have ever heard of invertible ID in your travels? How many of you have heard of the class? Ever heard that in your travels? Oh, you're in for a treat then. So let me start by the concept of what I'm going to call a fraction line. So definition. So I'm section 9.2. Invertible line goes. And since this is the last day of class, I might prove a couple of things. I find it fun to prove, but I'll probably kind of give you some facts and things. It's really more than anything else. That's 9.3. Actually, I can't read. Everything in here is an interval domain. So let R the domain with quotient to a K. An R submodule of K is a fraction line let me see. Let's call it some an R submodule I of K. It's said to be a fraction line deal if there exists a non-zero A and R such that A times I is an even R. Now, let me give you some examples of this. Now, R submodule quotient field means it's just some subset quotient field that's closed under multiplication by R. Fractional ideal is defined as condition, right? This allows me not to let things get too out of control. Let me point out a couple of things. Any ordinary ideal I and R is any ideal of a ring is a submodule, and it's certainly contained in the quotient field because it's contained in R. Agreed? And we have this condition because what if I is an ordinary ideal, what can you take A to be? Just take the V1. That's right. Right, agree? So this notion of a fractional ideal is a generalization of the ordinary ideals that you have. But this is a bigger kind of class of things. Here's another example. So 2 minus 1/2, 0, 1/2, 1, 3/2. Notice that this is an R submodule of quotient field C, namely the rations. So the rational numbers. It's certainly when you add two things, notice that every one of those things can be construed to having a denominator of 2, right? But -2 over 2. Notice that these are closed under addition. They're closed under multiplication from Z, right? And What A can I use here? What's a value of A that blasts this thing back into the integers? 2 will work. I could go crazy and do 64, but 2 works, right? And notice I like this example here because what this means, this condition means, is the stuff in a fractional ideal has a common denominator, right? Because what you're saying is I is a collection of fractions. When you hit it by A, it's down at R. So in other words, everything in I, you can collect them all to the single denominator A, or actually in multiple ways. Everybody okay? Notice one of the things that people think about ideals is you're used to thinking that when you multiply 2 elements of an ideal, they're still in an ideal, right? This isn't necessarily true here because, for example, 1/2 plus 1/2 is 1/4, right? But that's not weird because when you multiply 2 elements of an ideal, what you're really doing is you're multiplying an element of an ideal times an element of ring. Here you're cheating because you're multiplying an element of the ideal times something that's not, and that's where the problem is. If you know multiply any of these things by an integer, it's still in there. Everybody okay with that? Of course, Q is a Z submodule of Q. No problem there. Q is a submodule of a Z submodule of Q, but it's not a fractional ideal because there's no non-zero integer that will blast everything back into the integer, right? The problem is you got infinitely many primes. Okay, any questions on that? Okay, so this is the idea behind fractional ideals. They just generalize ordinary ideals. And so why would you want fractional ideals? Well, before I do that, I will confound you further, just for the moment, I hope, with this definition here. So again, my setup, my default today, everything will be a integral domain quotient field K. Let I be a fractional ideal of some integral domain. We define by the way, there's other notation I can use for this. This is the classical for fractional ideals, but this is actually a colon. This is called a colon operation. I inverse is the collection of stuff everything in the quotient field such that omega I is contained in R. So I inverse is the collection of everything in the quotient field that blasts I back into R. I know one thing that has to be in there. Well, certainly 0 has to be in there, right? Because 0 comes out, that's certainly an R. But whatever this A is, has to be in there. In fact, the condition fractional ideal guarantees that this collection of elements has something in there that's not 0. So this is stuff that blasts it all back into R. This is called the inverse phi. Let me point out that always it's the case that I inverse is contained R. Everybody agree with that? By the very definition of it, if you take anything that's an I inverse and you hit it with anything inside, it has to land in R. That's ordinary. if I inverse is equal to all R, we say is invertible. Okay, so let me give you some concrete examples. It's amazing how many times rings is a good stepping off point. Let's let I equal this ideal we have this invertible ideal. So we'll take a stab at what this is. Very good. Notice, let me point out that 1 isn't in there, is it? Right? 0 is, and so is 2, and any multiple. In fact, I inverse in this case is 2, 6. If you're going to blast everything back into R, you have to make sure that you're even. That's basically what that little mathematical thing is telling you there. Notice, in this case, I'm going to use this notation as a module. It's 1/2 Z because it's basically, it consists of 1/2 times every integer. Fine. I inverse is 2Z. Now, if you look at I inverse, I'm going to write this more generally than I need to. Right? You can do this much shorter for the this is the set of things that look like alpha 1 beta 1 plus alpha 2 beta 2. Alpha m plus beta m, where alpha I is in 1/2 Z and beta I is in 2Z. Correct. And these can be as long as short as you want. Actually, it turns out that you can always choose m to be 1 for this particular example because Z is the principal ideal. So notice that everything in here is, this can be written as 1/2 K1 to R1 plus 1/2 Km to Rm, which is of course in the integers, because all the 1/2s and 2's cancel, and this is just a linear combination of integers. And notice 1, which is 1/2 times 2, is in I inverse. So I inverse is equal to R. So this ideal is in fact invertible. Anybody got a nose generalizing this? So I did this specific example with this ideal I inverse. How about something more general? What are we domain? Always important. I think I should wait out an answer to this on the principle. How about that? It turns out any non-zero, I should say that, principle. Non-zero principle ideas are always perfect. So anybody want to take a stab at what the inverse of this idea will be? Okay. As it turns out, and it's easy to verify once I tell you. This is really no different in principle between our 1/2 business, right? And I inverse is equal to omega r, omega inverse r, which is 1 r. So all principal ideals are invertible. So look at me, look at me, look at me. I've developed this theory. I've got these things called invertible ideals. What is the next thing that I should do? Do you think? Suppose that this is brand new research going on. What's the next thing that I should do now that I've defined principal or defined invertible ideals? I've come up with examples. Well, okay. That's one thing I should do. Find something that's not invertible. And number two, and this is always an important check when you're a graduate student or a professor, or whatever you're doing, you must check that you're not a doofus, right? Because what would make me a doofus? If all this fancy invertible ideals were equivalent to principal ideals, then I feel a little bit foolish, don't I? Right? Why would I make all these definitions if all they are principal ideals in the first place? So there's two mountains to step over now. Is every ideal invertible? Actually, as it turns out, that one's an easy mountain to step over because it's actually a pretty rare occurrence for an ideal to be invertible. The other one, finding an ideal that's invertible by principle, is a little more delicate. But they exist in abundance when I show you. So here's an example. How about an ideal that's not invertible? Take any field. I'm going to let this be R. So K is, of course, this. Rational functions of two variables. Let M look at the ideal generated by both variables X and Y. Let's see if we can find that inverse of this. By the way, before we get too carried away, there's a fact I'm probably going to use along these lines here. I'm not going to, in view of time, I'm not going to be super careful with this, but I hope you get the idea that that's true. Does anybody know what the structure of the ring F, X, Y polynomials over? What's kind of the nicest thing you can say about that ring as far as properties that you know? It's not a principal ideal domain. Otherwise, this would be a real stupid example. If this was a principal ideal domain, that would mean that every ideal is principal. And, you know, we already know that all principal ideals are invertible, right? But this one does have unique factorization, right? And that'll be useful. So let's look at M inverse. This is the set of rational functions. So I'll write it this way. Now, quite abbreviated it. Such that okay, so this is all the rational functions that hit every polynomial maximal ideal and put them back in and make a polynomial, right? So in particular, right? And we can assume since the polynomial ring here is a unique factorization domain, we can assume that our fraction is reduced, right? So we can factor P, we can factor Q, and we cancel everything, and so all 2/3, no 4/6, right? We can cancel stuff out. Okay, so what do we get from this? Well, so we'll probably have to adjust this along the way, but what this means is X, now remember P and Q, these are polynomials. Right. Q and YP equals Q E double Q F. Right, where F and G are polynomials. This is equivalent to saying X P over Q is polynomial, Y P over Q is polynomial. Okay. So what can we glean for this? What do we know about the polynomial X? It's prime, isn't it? Right. So let me ask this: what happens if X divides Q? Right, because X divides this product here, and what happens if X divides F? Because look, both of these, or one of these, has to happen. What happens if X divides F? Well, if X divides F, that means there's a factor of X here, right? Which will cancel this right here. And that means that Q divides P, correct? And therefore, Q equals 1 up to a unit, right? Because remember, the greatest common product of these two is 1, right? What happens if X divides Q? Well, in this case, Y divides Q as well, right? Because if Y divides G, you've got the same problem you had before. You've got Q equals 1, which of course shows that you're in R, right? And so if both X and Y divide Q, then right, then you can reduce the fraction again and keep on going in this fashion. I am going like really kind of fast and loose here, but considering these factorizations, you get actually in the inverse is equal to R. It turns out that the only stuff, the only rational functions that knock all of them into R are just polynomials. So your denominator has to convolute. So in other words, it has to be a polynomial. And so notice in this case, in this case, what's going to happen is you're actually going to get a strict containment. And this is actually the most common thing. I mean, if I walk up to you on the street and give you a non-zero ideal in some domain, odds are it's not invertible. The trickier part is to give an example, non-principal and invertible. And actually, I'm going to get a theorem out of this as well. For this one, let's see. Let's look at this. Let's put R. I'm sure that many of you have played with this ring before, right? I mean, it's one that shows up like in the basic algebra class when you talk about things like factorization and so forth. This is the one that's got those weird factorizations, right? If you look at the element 6, and this ring is 2 times 3, isn't it? But it's also 1 plus radical negative 5 times 1 minus radical negative 5. So it's kind of a classic first example of, oh, look, we've got something that has factorization that's not unique. Well, let me build a couple of ideas. Yeah, I guess so. Let's move on. Now I'm going to show you something interesting about this ideal. First of all, I guess the first thing I should do is convince you that this is not a principal ideal, right? Because otherwise I'm just totally blowing smoke here. This is I is not principal. Let me prove it. Suppose now for this to be principal, well, actually, let's do this first. We show I. Okay. Because one thing that could go wrong is to be the whole ring. If it's the whole ring, it's generated by 1. Assume not. Then there exists, let's say, such that 2 if this ideal is the whole ring, then there must be a linear combination of 2 generators that gets you 1, right? So what the heck is this? This is 2a plus 2b radical negative 5 plus c minus 5d plus c plus d radical negative 5. Yeah. So equals 1. And so this gives me 2a plus c minus 5d plus 2b plus c plus d radical negative 5 equals 1. See the problem? Lots of letters to see the problem, but there's also. Let me show up my flare matic. You see the problem? You must see it here. Reduce it on that's essentially it. That's exactly right. What's that equations? Even equals odd. It's possible. So the idea is not profit, right? I'm sorry, the idea is profit. Okay. I also claim that it can't be singly generated. So I'm just, it's all set up here to show you that I've got a bona fide example. Now suppose that how many of you have ever worked with the norm on this thing? Right, the norm of this thing is this times its conjugate. It's sort of like rationalizing the denominator or rationalizing kind of things that you do. How many of you have seen this norm function before? Norm of alpha times beta is the norm of alpha times beta. The norm of alpha is 1 if and the norm of alpha is plus or minus 1 if and only if the element's a unit. The norm is 0 if and only if it's 0. And the important thing actually is the norm is multiplicative. So if alpha divides 2, then norm of alpha divides the norm of 2 is 4. Right? Because if you put 2 plus 0 radical negative 5, you get 4. So if this is generated by a single element, alpha has to divide 2. That means the norm of alpha has to divide the norm of 2, which is okay so far? Yes. No, because it's no, because you multiply by its conjugate. You get a minus, and it's like there's this plethora of minuses that cancel everything. If alpha divides 1 plus radical negative 5, then norm of alpha divides the norm of 1 plus radical negative 5, which is 6. Right? So norm of alpha divides 4 and 6. What are my choices here? So the norm of alpha is equal to 1 or 2. And clearly, no negatives are involved because this thing always barfs out things that are not negative, right? Okay, well, if the norm of alpha is 1, that's a problem because that means that that element's a unit. We've shown that this is proper ideal. So we must have the norm of alpha, which is a squared plus 5b squared, some choices of a and b equal to 2. And that is clearly ridiculous. Because even if b is 1, it's too big. So b has to be 0, and then you've got a squared is 2, which can't happen to the integer. So after all this work, hopefully We now believe that this is a proper non-principal idea. Everybody agree? However, its square is principal. I mean, is it really, that's kind of strange, isn't it? Because if you look at an ideal, like the ideal generated by X and Y, that you looked at in the M example, if you square that ideal, MX or XY times XY, you actually go from requiring 2 generators to 3. Because now you've got X squared, Y squared, and the XY cross term is generators of that ideal. If you take it to higher powers, you require more. If you take it to the 3rd power, you need the generator X cubed, X squared, Y, XY squared, and Y cubed. Here, you square an ideal that's obviously generated by 2 generators and it drops to 1. That's kind of weird. Let me verify that. This is now generated by 4. These terms are the same, so 2. And the square of this, which is minus 4, 2 rather than product of these two, product of these two, product of these two, and then the product of these two. And since they're the same generators, I don't require the extra cost. But it's, I claim that this is the ideal generator by 2. Now, no containment should be fairly obvious, and that's this one. 2 certainly divides every one of these. Right, the quotient is 2, 1 plus radical negative 5, and minus 2. The other containment is a little more subtle, but not too far anyway. To get this containment, it will suffice to show that this ideal actually contains 2. See, 2 is greater than or equal to this ideal. It contains this ideal. If you can generate a 2 out of this, you're good to go. Anybody see how to do it? Take this one and subtract this one, and you get 2 minus 4 is 6, and then these cancel out. Now you've got a 6 in there and a 4 in there, so you've got 2. So it actually can fall. That's really weird that it collapses like that, but it does. And so this is an example of an invertible ideal. I've just got one more computation to do. What I have now is I times I is equal to R in this case. Or I'm sorry, not R, but 2R. The idea generated by 2. Agree? So notice, multiply both sides of this equation by 1/2. And this piece right here functions as I inverse. Any questions on that? Questions? All right. Let me give you kind of a couple of things. Kind of take one with you. I'm not going to have too much more of your time, but I do want to prove one more theorem, which I think is really cool. And then I'm going to collect some so here's the theorem. Okay. I is an invertible ideal. Then I is finite determinant. I like to prove this theorem because it also gives you an idea of how to deal with ideas. By the way, the converse of this theorem is wildly untrue. In fact, the example that I gave you of a non-invertible ideal, that M in the polynomial ring, that's a two-generated ideal. So sort of constantly generated, but it's not invertible. But it's not clear, is it, from the definition of an inverse of an ideal, why it would have to be finitely generated, right? But it does. They have to be finitely generated. Proof. Suppose that I is generated by A1, A2, up to AN, where these are elements of the quotient field. Now, by assumption, I inverse is equal to all of R. Right? That's what we're assuming this idea is invertible, right? So what does that mean for I inverse to be equal to 1? So I'm assuming it's finite generated. Let I be our invertible ideal. My bad. I don't know why I wrote that down. I guess I'm trying to generate it for I inverse. Anyway, we don't know at the outset that it's inverted or that it's finitely generated. So I's are ideal, I inverses R. Everybody cool with that? So there exists A1, A2, AN, and I, and B1, B2, BN, and I inverse, such that A1, B1 plus A2, B2 plus AN, BN is equal to 1. Because a typical element by I inverse just looks like sums of products like I and N, right? And this is, I guess, this is why I made that clerical error at the beginning, because I was thinking about this. I claim I is I claim that A can be generated by that finite list of these ANs that show up in this equation. Here's the proof. So since that certainly must be the case, that since these things all live in I, then certainly the ideal generated by the, and when I say I should really say the module generated over R with this is contained in I. The tricky part's the other direction. Now suppose that alpha is an element of I. Okay. I want to show that alpha is a linear combination of these, right? Let's go back to our equation. Right. Now hit this with alpha. Now, can anybody tell me where these terms of parentheses live? Notice alpha is an I, and beta I is an I inverse. So alpha beta I is in right R. So alpha is an R linear combination of A1, and so I is equal to this. Here's one to kind of, if you want to kind of get good with this stuff, here's an interesting sort of one I'm going to give you a spin off theorem. If I in R is actually doesn't have to be A in R is an invertible ideal, and R is, I hate writing this. This just means it's got finitely many maximal ideals. So if R has finitely many maximal ideals, then I is principal. This is kind of, see if you can prove this actually. In fact, I would recommend that you do it just for this, the quasi-local case first, where there's only one maximal ideal. It's easier to do there before you go out to only finitely many maximal ideals. So I'm going to tell you about two more things, just kind of for your culture and knowledge. And the first is called a Dedekind domain. Anybody ever heard of that? Some of you? All right. Did I give you all my spiel about Miles' theorem earlier? I talked so very, very much. So yeah. How many of you know what Miles' theorem is? See a lot of hands on that, right? So Miles' theorem says this equation right here has no integer solutions, non-trivial. What I mean by x, y, z, obviously you've got the solution that x to the n plus 0 equals x to the n, right? But if you throw out the silliness, this has no solutions for n bigger than 2. For people, n equals 2 is Pythagoras. They parameterize the triplets there and so forth and so on. This can be reduced showing as no solutions for primes. You can actually reduce this. So instead of worrying about arbitrary integers, you can just worry about primes. You can reduce it down. So people started looking at this. Of course, 4 is not a prime, but there's a famous proof by a technique called infinite descent, where basically you build a solution and then you can show that there's a smaller one. Since we're talking about integers, it's ridiculous to, and that famously showed x is 4 plus y is 4 equals z. 4 has no solutions. Fermat himself did x cubed plus y cubed equals z cubed. Actually, supposedly after he wrote that thing in the margin, so probably realized later in his life that maybe it wasn't true, or maybe his theorem didn't work. Well, his theorem worked, maybe his proof didn't. So people started attacking this. And I think it was in 1847. And it was wrong. And the reason it was wrong, because in some things that you'll see. Based on the assumption that this ring here, where this is a cyclotomic ring of integers. Remember, we looked at cyclotomic fields ever so briefly. We were joining roots of unity. Right? This is the ring of integers of that field. Right? It's all things that satisfy my common C. For every prime for which this is a UFD, you can prove this. And it was, people thought that this thing was, didn't matter what the prime is, it's always UFD, right? They're all the, and of course you can see the importance here, because if you've got this ring with a ring of integers in it, what you can do is you can factor this as X plus. Maybe I need to pick it over to the other side, but anyway, you can factor this down. You can argue that either all of these have to be a peak power, and you go through some machinations, you get a contradiction. This assumes that you can factor uniquely into prime elements. You can't. The first prime, anybody know the first prime it fails for? That is correct. 23. At 23, this thing fails, and so, well, we're good to go up to that. I'm right, we're good all the way up to and including 19, and then it fails up to that. Actually, kind of is a funny sort of side. It turns out it's okay at 23 anyway, even though 23 doesn't have unique factorization, because they came up with something called regular and irregular primes. Regular primes are ones that don't divide the order of their class group. And I'm going to tell you what that is in just a moment, very briefly. So with all the lower primes in 23, the class group is 1 and the primes are regularly divided. The class group of P was 23. I think this is Z3, order 3, 23 doesn't divide 3. This one's good to go. So now it's proved not just for the UFD ones, but for the regular ones. Since then, Andrew Wiles has done it, and the research kind of went off track of that. But rather ironically, I think that they probably named regular primes too soon, because the last that I read, it is known that there are infinitely many irregular primes. It's not known that there are infinitely many regular primes. So that seems about premature nomenclature there. But this was a problem, and there was an easy solution until the problem was discovered. One can argue that this gave rise to something called Dedekind domains. So definite, what are a domain? The following conditions are equivalent. Number 1, every non-zero ideal is invertible. Number 2, every non-zero fractional ideal is invertible. Number 3, R is Noetherian. And R localized P is a Noetherian. You don't need this word, it's automatic after the first assumption. Valuation domain. for all prime ideals P. Number 4. Every proper non-zero ideal I contained in R proper is uniquely a product of prime ideals. So notice how we get around this problem here a little bit, not perfectly. In this ring, you might or might not have unique factorization of elements of prime elements, right? Sometimes yes, sometimes no. But in all those rings, every last one of them, all the ideals factor uniquely into prime ideals. And 5, R is Noetherian, one-dimensional, well, less than and integrally closed. So, by the way, dimension 0 means field, so that's something I won't think about that too much. In Noetherian, all ideals are finitely generated. All non-zero prime ideals are maximal ideals, like the integers 0 to 2, 0 to 3, 0 to 5, and integrally closed. Then you will automatically get all these other products. Let me kind of show you in a quick example here. In fact, every ring of algebraic integers has this property. Any ring that satisfies one, hence all of these, it's called a Dedekind domain. Okay, so let me give you a quick example to show you some of the pairing off about. So how many of you have seen that factorization? This is a non-unique factorization of elements. However, there's a unique factorization of prime. So let me give you a list of ideals. You've already looked at this ideal here. It turns out, so you can check this yourself, it's fun. The ideal generated by 6 in this ring is P2 squared 3 bar. Just take these ideals and multiply their generators. 2 copies of the first one and then the last 2 multiply together, and you will get the ideal generated by 6. We'll get 6 in that ideal and 6 will by their P. Where does this come from? Well, how do you get the different element factorizations? Well, it turns out that 6, so, and actually I'm going to screw this up probably. This is equal to P2 squared. That's the ideal generated by 2. And P3 bar. Check me on that. It's easy for. Where does the other one come up? And I forget which is which. I always get this turned around when I do it. But multiply these two and see whether it's divisible all by 1 plus radical negative 5 or its conjugate. So see what happens is it's like a combinatorial problem. It turns out the product of any two non-principal ideals in this particular ring is principal in this particular. And so you've got 4 ideals there. You can deal them out in a couple of ways. 2 P2s, and then this pair gives you 2 times 3. A P2 and a P3 and a P2 and a P3 part. Another one. And those are the only ways to distribute that. So we're getting close to doing class group, but I think that's probably enough time for today. But if you're curious about this sort of stuff, then come give me a holler. Any questions about any of this? Well, if you're still finishing up your homework,